saw consistently like the same kinds of mistakes over and over was on number 8. So specifically when dealing with simplifying the radical, so people, never ever ever can you break a radical at an addition or subtraction symbol. It's like doing this kind of thing is never ever ever really never going to be okay. Nor does just like, can you do something like this and cancel just one from one place and do stuff like that? That's like a bunch of made up gobbledygocks. Realistically, the answer for 8 should have just been square root and then underneath 36x squared minus 31, which most of us had at one point, and then we just went overboard with our made up simplifying and like bulldozed past the correct answer into like made up math land.
Why couldn't you pull a 6 though? 6xs?
Because you can't break a radical at an addition or subtraction symbol. Because the 6 doesn't, can't take a 36 out of 31. Like if you wanted to do that, you could, what you'd have to do is factor a 36 out, and then you could do 6 square root x squared minus 31 over 36, and that would be okay. But that's way worse than it would have been when you had the original, right? Yeah, a lot of people did this breaking their radical at the addition and subtraction symbol, which just makes your math teacher sad. The other place that almost nobody came up with the correct answer was on 14. And the issue there is when we talk about that general form for a transformation, notice the c has to be factored out. It has to be like a coefficient of the x minus h. So here, you would need to start by factoring the 4 out. So the h here is really -2 and not -8. Almost everybody missed that. Few people here and there caught it, but almost everybody missed that. So that's the other piece that I want to make sure that we touch on, because it's a little thing, but it's one of those things, if I don't point this out and it keeps happening over and over and over again, like this will happen many times where you just didn't get it into the general transformation form before you started identifying the A, C, H, and K's. And then you goofed up the H, which is really easy to do. So those are the 2 most common mistakes that I saw on these. Again, I'll have that answer key that I'll dump into the content library here later this week, probably tomorrow. And you can go through and look at specifically, worked out solutions for things if you care. At this point, maybe some of us are like, yeah, you know what, like I did fine, like a couple of doodly-doos here and there, like, oh, I forgot a plus or minus, or oh, I did something silly, or oh, yep, just forgot what to do on that, but like I know what to do. Okay. All right, so let's talk about the rest of the week's plan. Today we're going to do section 2-4. That'll close this chapter 2. That's the last section in chapter 2. And that'll probably take, 45 minutes or so to do that. The rest of the time here in class, I'm going to give you to work on the homework sets. Wednesday we'll take as a review day. We'll just work on the review or whatever you have to do for your homework set. Friday, we're not going to do the test because, quite frankly, the day before homecoming, who wants to worry about taking a test? We'll just start chapter 3, and then Tuesday of next week we'll do the chapter 2 test. So, everybody feel okay on that?
I still have a test, though.
Well, not for me though, because Mr. Kulik cares about your mental health and is going to try to make life just a little bit easier for you by doing it.
Thank you. It's a busy weekend.
Yeah, so I get it. Again, So that's going to be the plan. Everybody happy with that?
Yeah.
Okay. Yep. And again, all the assignments in the calendar on My Notre Dame should reflect all of that. So again, there's a lot to do for the homework set, but like, you know, you have a class and a half to take care of things, and it's not that big of a deal.
Would the chapter 2 review probably be due on this Sunday? Okay, take it there.
Drake.
I understand what you mean now.
Did you really just have to change the minus signs to plus?
No, you had to do f of negative x.
Oh.
So just the degree 1x's coefficient changes sign. Okay. So let's bang out section 2.4 here. And this is this is like the most important section of this chapter. So what we've been working on, or what we had kind of talked about on the first day, is one of the things we need to do in this first semester is to build out these definitions of sine, cosine, and tangent so that they're not reliant on a right triangle so we can do sine, cosine, and tangent of non-acute angles, or even angles that are bigger than 180 degrees or less than 0. And in section 2.3, we took our first step towards doing that when we defined like an angle that, or these angles of rotation, these standard form angles. Because now we can represent angles of any size, right? As big as you want, as small as you want, we can now have a representation of what that angle means. And what we're going to do now is we're going to use that new representation and generalize our SOHCAHTOA definitions of sine, cosine, tangent, etc., and move out of right triangles and onto these angles of rotation. So that's kind of the goal for today. And the way that we're going to do that is we're going to start by saying, okay, like we have some angle of rotation. I'm going to pick some point on that angle of rotation. So that point has some coordinate xy. What I'm going to do is I'm going to drop a perpendicular back down to the x-axis. So I'm going to call those points M and then O for the origin. So what have I just made? A right triangle, right? So this triangle PMO is called a reference triangle. And this angle, I'm going to call, that's formed between the terminal side and the x-axis, I'm going to call alpha. So that's the Greek letter alpha. It looks like a little Jesus fish. That is called the reference angle. And what's really valuable about these reference angles is that trig of, or sine, cosine, tangent, etc. I'm just going to write trig because it kind of applies for all of them. Sine, cosine, tangent, cosecant, secant, cotangent. Rather than writing this relationship 6 times, I'm just going to use trig to represent all of them. So if I do sine, cosine, tangent, etc. of theta, it's almost exactly the same as sine, cosine, tangent, etc. of this reference angle. I just have to make one little minor modification with whether these things are positive or negative. So that's what the little asterisk there is for. Lexi?
What's after reference with the triangle PMO?
That's just the symbol for a triangle.
Okay, it's just a triangle.
Yeah. It's just bad penmanship. That's a little bit more pointy. Okay. So let's go back to this. Yes, Sergio.
Oh, sorry for the back, but after you put the break, like the little thing like that, like not the exponent, but like what is that? I like that alpha thing.
Just a little asterisk.
Oh, okay.
So let's look back at this reference triangle now, and let's assign some values to these side lengths. So the side length MO should have what measurement? Well, it would be negative, but more specifically, it would be x, right? Why? How do you plot a point? You go x units over, and then you do like y units up. So MO should have length x, and PM should have length y. Now, in this current orientation that we've drawn, that x coordinate is negative, so we're going to allow the reference triangles to have negative side lengths to account for that. Everybody's okay with that? All right. Now, let's use this reference triangle to determine our values for sine, cosine, tangent, and then cosecant, secant, and cotangent. So, if I look at that reference triangle using angle alpha, opposite is y, and the hypotenuse, what would the hypotenuse be in this situation? Be the square root of x squared plus y squared. Why is that? It's the hypotenuse of a right triangle, so by the Pythagorean Theorem, I know it's equal to the sum of the side, or the hypotenuse squared is equal to the sum of the side squareds. But I don't want to write that mess down. I'm just going to call that r. So sine should be y over r. And cosine then would be adjacent over hypotenuse, so x over r. Tangent is opposite over adjacent, so y over x. Cosecant is the reciprocal of sine, or hypotenuse over opposite. Secant is the reciprocal of cosine, or hypotenuse over adjacent. And cotangent is the reciprocal of tangent, or adjacent over opposite. Now, what we've done here is we've translated our definitions of sine, cosine, and tangent from being specific to a right triangle. Now they're in terms of the coordinates of some point on the terminal side of an angle in standard position, right? Now these definitions, y over r, x over r, y over x, etc., this is still basically just SOHCAHTOA, right? Just instead of saying opposite, we're saying y. Instead of hypotenuse, we're saying r. Instead of adjacent, we're saying x. But the language is now different, right? So this is super valuable. This is our very first step towards kind of the final resting place for how we're going to define these things. Because we've now moved outside of the right triangle definition into a standard form angle definition. And is that something you should remember? These new definitions for sine, cosine, and tangent, etc.? You betcha. The good news is that they're not much different than SOHCAHTOA, right? all you have to do is remember that like opposite is y, adjacent is x, and hypotenuse is r, and it's still the same thing, but so let's say we have the point -3, 4 that lies on the terminal side of theta. And we want to evaluate the 6 trigonometric ratios for theta. Well, let's draw ourselves a picture of kind of what's going on real quick. It's not really necessary to draw the picture, but this is the first time, and I think usually having a visual aid helps a little bit. So we'll draw our standard position angle. So the initial side is always there on the positive x-axis. Then if I plot the point -3, 4, I'm here. I'm going to make my right triangle, or my reference triangle. I'm going to label the side lengths using x and y. Remember, the x-coordinate is always the part that's on the x-axis, and the y-coordinate is always the part that's up and down. When we make our reference triangle, it's worth noting that we're always drawing to the x-axis, never to the y. That's an important point to make. So our r in this case is going to be 5. Oops. 5, not square root 5. Square root 25, which is 5. Everybody so far so good? Okay. So now sine is, yeah. 16 plus 9 is 25.
Oh,
And the square root of 25 is 5.
makes sense.
Not the square root of 4 plus the square root of 3, because you can't do that,
Okay, fine.
right? Everybody's good with sine being 4 over 5? And cosine theta then would be -3 over 5. Tangent is going to be y over x, so 4 over -3. Cosecant theta is the reciprocal of sine, so 5/4. Secant theta is the reciprocal of cosine, so -5/3. And cotangent theta is the reciprocal of tangent, so -3/4. There's that. Not too bad, right? You're basically just using some new formulas, but it's really no more difficult than SOHCAHTOA. The thing you need to be careful about is making sure you're including those negative signs, but that's not so bad. What if we wanted to find the value of cosine of 150? Well, let's start by drawing our picture of 150 degrees. So far, so good. Pick a point, make my reference triangle. So this reference angle here has to be what measure? $30 degrees, right? because we know straight line is 180. We've done 150 of it, so there's 30 degrees left to go. Okay? So this angle then up here has to be 60 degrees. And what we have is a 30, 60, 90 triangle, one of these special right triangles. Well, I know the ratio of side lengths for these. But what's the one thing I have to be careful about here? The sines. What quadrant is my angle or my point in? The second quadrant. The x-coordinate in the second quadrant needs to be negative, so the part on the x-axis needs to be negative. Is everybody okay with that? That's the easiest place to make a mistake, is just forgetting what quadrant you're working in and dropping your negatives. Be careful on that. Now that we've done this, though, cosine of 150 is just going to be adjacent over hypotenuse. So we have negative root 3 over 2. Is everybody happy there? That's just adjacent over hypotenuse from the triangle that we drew. Amy? So our point is in the second quadrant, right? Any point in the second quadrant is going to have a negative x-coordinate and a positive y-coordinate. So we need to make sure that we're representing as much with our sides. Mm-hmm. Okay. One more step now. So we've done this, right? At this point, we've been just kind of picking this point P to be anywhere on the terminal side. We're going to standardize that a little bit now. And from now on, we're going to pick P so that the distance from P to the origin is 1 unit long. Okay with that? So if I just let P rotate along, what kind of shape is going to be made by the locations of P? Yeah, it's going to make a circle. Everybody kind of agree with that? Oops. So what we call this then, that circle formed, is called a unit circle, because the radius on that circle is 1 unit. in length. Now, in combination with what we saw in the previous example with the cosine of 150, I know that anytime I make a standard form angle where the reference angle is either 30, 60, or 45 degrees, I can use my special right triangles to calculate the exact value for that angle measure. Everybody's good with that? So what we're going to do is we're going to, instead of doing that same process over and over and over again, we're going to create a shortcut so that whenever we have to take the sine, cosine, or tangent of one of these kinds of angles, we have like a shortcut. We can just go straight to the answer instead of having to draw the picture and figure everything out. So we'll start with this. This is the unit circle blank. This is in your content library also. You don't need to fill this out on your own. We're just going to do it together right now on our own. Okay? So we'll start here. This is 0 degrees, also 0 radians. The point here, the x and y coordinate would have to be 1, 0. Again, if we know the radius is 1 and we're flat on the x-axis, got to be that. Next is 30 degrees, or pi over 6 radians. So I know if I draw my 30, 60, 90 triangle, there's that. The hypotenuse of that 30, 60, 90 triangle is also the radius for my circle, so I know that that has to have length 1, which tells me the x has to be length 1/2. Everybody's okay there? So my x side is √3/2. And my y side is 1/2. Everybody's okay there? Over here at 150 degrees, I also form a reference angle of 30 degrees, correct? That's the same thing as 5 pi over 6. So the x-coordinate would be the same thing except negative, because we're in the second quadrant, and the y-coordinate would just be the same. Here at 210 degrees, we're also going to have a 30 degrees reference angle. 210 is also the same thing as 7 pi over 6. In the third quadrant, the x and y coordinates are going to be negative. And then all the way over here at 330 degrees, or 11 pi over 6, also makes a 30-degree reference angle. Here the x-coordinate is positive, but the y-coordinate is negative because we're in the fourth quadrant. Everybody okay with that? Well, let's do the 60-degree angle also. So again, I'm just drawing kind of the same 30, 60, 90 triangle, except this time the x-coordinate is 1/2 and the y-coordinate is √3/2. And so I march around the unit circle, filling these other pieces in. So also over here at 120 degrees has a 60-degree reference angle. That's 2 pi over 3. So that would be negative 1/2, and then root 3 over 2. And then also over here at 240 degrees, or 4 pi over 3. Both the x and y coordinates are negative because you're in the third quadrant. And then over here at 300 degrees, or 5 pi over 3, the x coordinate is positive, but the y coordinate is negative. Everybody so far so good? I guess I should have filled in the rest of these quadrantal ones, huh? 90 or pi over 2 is 0, 1. Negative 1, 0 is 180, also known as pi radians. 0, negative 1 is 270, or 3 pi over 2 radians. Sorry, I should have done that in the beginning when we filled out 0 degrees. And then the last one I need to do is the 45, 45, 90 situation. So x, x, and then x root 2. Again, I know that that hypotenuse has to equal 1. So that tells me x has to be 1 over root 2. So 45 degrees, or pi over 4, 1 over root 2 for both. And then this is going to be 135, or 3 pi over 4. So I have 1 over root, or negative 1 over root 2 because we're in the second quadrant, and then positive 1 over root 2. 225, or 5 pi over 4. That'll be negative 1 over root 2 and negative 1 over root 2 because we're in the third quadrant. And then 315, or 7 pi over 4. That'll be 1 over root 2, negative 1 over root 2 because we're in the fourth quadrant. Yes, sir?
Can you just simplify the 1 over root 2 to 1/2?
You can write 1 over root 2 as root 2 over 2.
Oh yeah, root 2 over 2.
I think is what you probably meant. Yep. And in fact, I give you also in the content library the unit circle with everything filled in. And I've gone ahead and rationalized denominators for those in that situation. Everybody's okay with that? Now, if you do that, you don't really have a unit circle, because if you did like the Pythagorean theorem, you're not going to come out with 1 as the radius, but like it doesn't really matter. Okay, so we have this unit circle. So let's show you guys a little bit on how we're going to use that to shortcut through some stuff. So let's do a little example here. Oh, yeah, a little bit of, before we do that example. So we have this unit circle, right? So before we said that sine theta was going to be y over r, but if r is equal to 1, sine theta is just going to be the y coordinate for my unit circle, right? Everybody's good with that? Similarly, cosine theta, which we said was going to be x over r, well, that means cosine is just x. Tangent didn't involve r, so let's not bother to write it. It's still going to be y over x. Cosecant theta was r over y, so that's going to turn into 1 over y. Secant theta was r over x, so that's going to turn into 1 over x. And then cotangent doesn't involve an r, so it's just still x over r. Or x over y. So this is now as simple as we can make it, where we've dropped the r out of there. This definition now involves only x and y, since r is just 1 the whole time. Okay. So we're going to use the unit circle then to evaluate some of these trig ratios. Okay. So let's say we want to do sine of 120. So first thing I'm going to do is find 120 degrees on my unit circle. I know that my unit circle definition for sine of theta is y. So I'm just going to read the y coordinate off my unit circle, and that's my answer. That's pretty easy, right? If I want to do tangent of 5 pi over 4, let's locate tangent of 5 pi over 4. Right there. I know tangent is y over x. So the y coordinate is negative root 2 over 2, and the x coordinate is negative root 2 over 2. So when I simplify that down, I just get 1. Very nice. Cosecant of 390 degrees. Uh-oh. 390 is not on my unit circle. What do I do? So I find the coterminal angle to it, right? If the angle or the value of sine, cosine, and tangent is just dependent on the location of the terminal side, an angle and its coterminal are going to have the same values, right? So cosecant of 390 is going to be the same as cosecant of 30. So I find 30 degrees. Cosecant is 1 over y. Or just 2. You guys feel good about using the unit circle? Pretty useful, right? Makes life quite a bit easier than having to draw those reference triangles and remember your 30, 60, 90, and 45, 45, 90 triangles. But that's all this is. It's just a time-saving shortcut from having to do that, all that drawing and labeling and remembering those side lengths again and all that nonsense. One more example, and I'm all set for today. So we want to find the value of sine theta if cosine theta is equal to 5 over 7 and cotangent theta is negative. Okay. So I'm going to start by kind of drawing us a picture because, again, the first time we're doing this, we don't really need the picture, but I think it helps get a sense of kind of what's going on or why this problem's going to work if we have the picture. So I remember that cosine theta is x over r. Everybody's okay there? So there's two possible angles that I could be talking about. I could be talking about this angle, or I could be talking about this angle. Either place, the x-coordinate is positive, and the radius or the hypotenuse is always a positive value. So the x's and y's can change length, but the radius can't with the convention that we've set up. So how do I know which angle I need to use? Well, the cotangent is going to tell me. So remember, cotangent is x over y. We know the x value is already positive because the x value is 5. And since that fraction is negative, I know for a fraction to be negative, either the numerator or the denominator have to be negative, but not both. So that tells me the y-coordinate is negative. Everybody good with that? So the situation I want is this one where the y-coordinate is negative. Everybody's good with that? Yes? Okay, so I know that x over y is negative because cotangent is negative.
Oh, yeah.
And if x is positive and x over y is negative,
Oh.
y has to be negative, right? So just using like basic positive negative argument there, right? So how am I going to find the value of that side? How about just with the Pythagorean theorem? Everybody's good with that? 7 squared is equal to 5 squared plus y squared. And to do the square root of 24, I can rewrite that as square root 4 times square root 6, or just 2 root 6. So I can say then sine theta is opposite over hypotenuse. Everybody okay there? Alternatively, another way we can do this without having to draw the picture at all is to think about things this way. So I know in the first quadrant, both the x and y's are positive, right? The second quadrant, x is negative, but y is positive. The third quadrant, they're both negative. And in the fourth quadrant, x is positive, but y is negative. Okay. So in the first quadrant, all of our trig functions are positive because x and y are positive in both, or both are positive in that location, right? In the second quadrant, the only trig functions that'll be positive are the ones that contain only s and r, which is sine, and then also, obviously, its reciprocal, cosecant. In the fourth quadrant, or I'm sorry, the third quadrant, the only ones that'll be negative are the ones that contain both x and y, because x over, negative over negative is positive still, right? So that's tangent and its reciprocal, cotangent. And then in the fourth quadrant is going to be positive that contains, or the only functions will be positive are the ones that contain only x and r, which is cosine and its reciprocal, secant. So back when I was a student, the way that the acronym that we used to remember this was ASTC, ASTC. And we said that all silly turtles crawl. You can make up your own acronym that's easier to remember for you. This makes little sense to me, but I remember it still from 30 years ago when I was a student. Well, 25 years ago anyways. But I still remember it. So what we can do with that is it can tell me where cosine is positive. That's the first quadrant and the fourth quadrant. And then cotangent is negative in the second quadrant and the fourth quadrant. So I know that theta has to be in the fourth quadrant because it's the only place where both of those things can happen. And I can do that then without having to really draw a picture, right? I don't have to draw both triangles hypothetically and figure out which one is which. I go straight to the triangle that I need. What do you guys think? Okay. Well, that's, yes, sir.
Why would the 2 turn negative and the answer for the sign?
So we had figured out right here that the y coordinate is negative. That's why I put the negative sign right there. And then I figured out what the length was using the Pythagorean Theorem.
Okay.
Is that okay?
Yep, thank you.
Yeah, no problem. Again, like these little details about things being negative and positive, we just have to be very careful. Trig gets rather detailed about stuff like that, where we put a negative value in there for a reason and not necessarily like an algebraic reason, but a geometric reason. And it's sometimes easy to forget those. Okay, that finishes off the sections. So you guys should be able to finish 45 through 60 from the homework. I also included 2 worksheets here for some more additional practice. So worksheet 1 is just evaluating things with the unit circle, so just practice using the unit circle. The hardest part will be like finding the angle coterminal that's on the unit circle to read it off, but it's not so bad. I have the worked out solutions with it, so you can always check. And then the second page is doing some more practice like that example we just finished with. So again, you can practice a little bit more with that. And then worksheet 2 is some transformation practice. So this was a place where on the first test we seemed a little bit shaky on, so I made some more practice on that. So again, these are just like find the values for A, B, H, and K, or AC, H, and K, and then write the transformation. And then like, do the transformation to the graph, and like do them in the order that we said. So just a little bit more practice on that kind of stuff before while we're at it. And again, I have the key written out for that stuff also, so it's should be okay there to check as we go. I'm going to stop now and get out of your